Today we will learn how to determine polar and nonpolar molecules. First, let's take a look at our question and how we would go about solving the question. We're asked, how many of these molecules are polar? The first step would be to draw the Lewis structure for the molecule. Once we have the Lewis structure, we can then determine partial charges on each atom, and we can determine the bond dipoles and which way they point in the molecule. The Lewis structure will also help us determine the molecular and domain geometry for the molecule. This will help us determine the net dipole for the molecule. Step 2, we will determine the partial charges. The partial charges are important because they will help us determine the bond dipoles. The partial charges can be determined by the electronegativity trend in the periodic table. The more electronegative atom will have a partial charge that is negative, and the less electronegative atom will be partially positive. This is due to the drift of electrons towards the more electronegative atom. Step number 3, we will determine the bond dipoles. This is important in determining polarity of the molecule because it lets us know where the electrons drift in the molecule. Step 4, we will determine the domain and molecular geometries. This is the last step in determining the polarity of the molecule because we can look at the domain geometry and the molecular geometry and determine if the bond dipoles will either cancel or they will be a net dipole. If there is a net dipole, the molecule will be polar. If the dipoles cancel, there will be no net dipole and the molecule will be nonpolar. Now let's take a look at the SO3 molecule. So first we will draw the Lewis structure, but before we begin drawing the Lewis structure, we must determine how many electrons will go into the structure. So, we can find the amount of electrons by adding all the valence electrons of each atom in the molecule. So we see that the S molecule will give us 6 electrons. The 3 O atoms each have 6 electrons, and these added together give us 24 electrons. Now let's see where all the electrons will be placed. The central S atom is bonded to each O atom with a single bond. Each bond is a covalent sharing of 2 electrons. So we see here that we have used 2, 4, 6 electrons already. After we use those 6 electrons, we have 18 left. The next step in completing a Lewis structure is to make full octets on the outside atoms. So now we place the electrons on the O atoms. So we have 2, 4, 6, 8, 10, 12, 14, 16, 18. So we used 18 electrons. Now we have 0 electrons left over. Well, the central S atom still is not a full octet. It only has 6 electrons. So now we must create a double bond on one of the O atoms to complete the central atom's octet. The SO3 Lewis structure will look like this after the double bond is placed. Notice that the 2 electrons that were on the outside of the O atom are now shared between the central and S atom and the O atom. Now let's look at the domain geometry for the molecule. We see that the central atom has 1, 2, 3 domains. So the molecule will have a domain geometry of trigonal planar. Now that we know the domain geometry, we now know how the molecule will actually be shaped. Now we're going to determine the partial charges. So we know based on the electronegativity trend in the periodic table that O is more electronegative. So now we know that the O will have a slightly negative charge, partial negative charge, because the electrons will drift towards each O atom. And then this will create a partial positive charge on the central S atom. We indicate the partial charges by these symbols. Now that we have the partial charges, we can now determine the bond dipoles. So we see that each bond dipole has a positive tail on the S atom that has a partial positive charge. The bond dipoles then extend out towards the O atoms that have a partial negative charge. The bond dipoles are shaped this way because it shows which direction the electrons are pulled towards. Now that we know the partial charges and bond dipoles, we can determine if there is a net dipole. We can also use the domain geometry to help us determine if there is a net dipole or all the dipoles will cancel. Because all three domains of the molecule are the same, there is an equal pulling of electrons in the molecule. So all of the bond dipoles will cancel and there will be no net dipole, so the molecule will be non-polar. We can also take a look at the vectors that the bond dipoles will make. We see that the two O atoms at the bottom are being pulled down into opposite directions. So those dipoles that are going in opposite directions will cancel. But there's still a bond dipole that is going down. But in the third domain, there is an O that is pulling electrons in the upward direction, and those two bond dipoles will cancel. Again, showing that there is no net dipole for the molecule, and the molecule is non-polar. Now let's take a look at the OF2 molecule. We'll begin by, again, drawing the Lewis structure first. Let's take a look at the valence electrons. We get 6 valence electrons from the O atom and 7 valence electrons from each fluorine atom, and when we add those together we get 20 electrons. Now let's see where these electrons will be placed. We will use 4 electrons in the bonds between the O and F atoms, 2 for one and 2 for the other. We subtract these electrons from our total, which gives us 16 electrons left. We will place electrons on the outside F atoms to create full octets. Now let's count how many electrons we used on the outside atoms. we use 2, 4, 6, 8, 10, 12 electrons. We subtract this from our remaining 16 electrons, and that leaves us with 4 electrons. Now we will use those to place on the central atom to give it its full octet. Now that we have the Lewis structure completely drawn, we can determine the domain and molecular geometry for the molecule. So we see that the central atom has 1, 2, 3, 4 domains. The molecule will look something like this. It has 1, 2, 3, 4 domains. Now the domain geometry is a tetrahedral, but because there are 2 non-bonding pairs in their own domain, the molecular geometry is bent. Now that we know the geometry, let's take a look at the partial charges. Fluorine is the most electronegative atom, so it will have a partial negative charge. The O atom is less electronegative, so it will have a partial positive charge. So the electrons will drift towards the more electronegative atom, which is the fluorine atom. This gives it a partial negative charge. Now let's draw the bond dipoles. So the bond dipoles will have a positive tail towards the O atom, which is slightly positive, and will extend towards the partially negative fluorine atom. Now let's use the bond dipoles and the domain geometry to determine if this molecule is polar or not. So we know that the molecule has 4 domains and is a tetrahedral. This will create an unequal pulling of electrons, so there will be a net dipole. This means that the molecule is polar. Now let's take a look at the beryllium chloride molecule. Now let's take a look at the electrons that we will use. We get 2 valence electrons from beryllium plus 7 electrons from each chlorine atom, and added together that gives us 16 valence electrons. We will now use this in the Lewis structure. So we have used 4 electrons in the bonds between the beryllium and chlorine atoms, 2 for each bond, and we subtract that from our total amount and we have 12 left over. Now we are going to make full octets on the outside atoms. So after we place the electrons on the outside atom, we have used 2, 4, 6, 8, 10, 12 electrons, and we are left with 0 electrons. We won't make double bonds between the beryllium and chlorine atoms because beryllium is an octet violator and can have a full octet without 8 electrons. Now let's take a look at the molecular and domain geometries. Beryllium has 2 domains, so the domain geometry is linear, and the molecular geometry also happens to be linear. Now let's take a look at the partial charges. We know that chlorine, being close to fluorine, is more electronegative than beryllium. So the electrons will float towards the chlorine atoms, giving it a partial negative charge. And this will create a partial positive charge on the beryllium atom. Now let's take a look at the bond dipoles. We see that the bond dipoles have a positive tail next to the beryllium atom, which is slightly positive, and it extends out towards the chlorine atom in different directions. Now let's take a look at the domain geometry and the net dipole. Because the domain geometry is linear and both domains are the same, the bond dipoles will cancel and there will be no net dipole. Therefore, this molecule is nonpolar. Now let's take a look at CCl4. We will start by drawing the Lewis structure and calculating the electrons that we will use. So we see that we get 4 valence electrons from the carbon plus 4 times the 7 valence electrons from each chlorine atom. These two added together give us 32 electrons. So we see that we are going to use 8 electrons, 2 for each bond between carbon and chlorine. We subtract these 8 electrons from the original 32 and we have 24 electrons. Now we are going to place electrons on the outside atoms to create full octets. So after placing the electrons on the outside atoms, we use 24 electrons. So we have 0 electrons left over, and the carbon atom has a full octet. So now we can look at the domain and molecular geometries. So we see again that the chlorine atom, being next to the fluorine atom, is more electronegative than the carbon atom, so the electrons will float towards the chlorine atoms, giving it a partial negative charge, and the central carbon atom will have a partial positive charge. Now let's look at the bond dipoles. We see that the bond dipoles all have a positive tail next to the carbon atom, which is slightly positive, and they extend out towards the slightly negative chlorine atoms. Now let's take a look at the domain geometry and dipoles to figure out if the molecule is polar or nonpolar. The domain geometry is a tetrahedral and all the domains are the same. Therefore, all of the bond dipoles cancel, so there is no net dipole. This makes the molecule nonpolar. Now let's look at the ozone molecule. First, we will draw the Lewis structure. We begin by counting the valence electrons that we will use in the Lewis structure. So each of the O atoms will give us 6 valence electrons. So 3 times 6 equals 18. We will now use the 18 electrons for the Lewis structure. So we use 4 electrons, 2 from each bond, and we subtract those from our total, giving us 14 electrons left. Now we will place electrons on the outside O atoms to create full octets. Now that we have a full octet on the outside atoms, we still don't have a full octet on the central atom and we ran out of electrons. So we will have to make a double bond with one of the O atoms on the outside. Now that we have the Lewis structure, we can determine the domain and molecular geometries. So we see that the central O atom has 1, 2, 3 domains. Therefore, the domain geometry will be trigonal planar. But one of the domains is a non-bonding pair and is different. So the molecular geometry will be bent. So this is what the molecule will actually look like in a bent shape. And from the domain geometry, which is trigonal planar, the molecule has one domain that is different, so the molecule will be polar because the dipoles do not cancel and there will be a net dipole. So now we see that there are 2 polar molecules that were given in our list. And that is all for the question. Now let's take a look at some common mistakes. The first common mistake is placing the electrons incorrectly and not knowing the octet violators. If you place the electrons incorrectly, it may affect the domain geometry because you may put too many electrons on the central atom, or maybe you didn't make a double bond. And if you don't know the octet violators, you might try and make a double bond, or you might be confused when the central atom has more than 8 electrons. The second common mistake is not knowing the electronegativity trend. If you don't know your electronegativity trend, this can create confusion when you are trying to draw the bond dipoles, and so in the end you get confused on if they cancel or if they don't cancel. The third common mistake is not knowing the geometries. So even if you didn't use the electronegativity trend and draw the dipoles and you base the polarity off of the domain geometry, if you get the domain geometry wrong, then you get the polarity wrong. And that is how you determine the polarity of a molecule.